let us wait for another 5 minutes maybe, and after that we'll start the session. Um, have you gone through this week's material? Let me ask you.
Not yet.
All right.
Not yet. I'm from mechanical disciplines.
Yes, sir. Tell me.
Uh, Whether it will be easy for us to go through these programming aspects?
Uh, I'm I'm not sure if programming aspects are asked, so that
Okay.
shouldn't be any problem.
Thank you. Thank you. Hope shortly people will join.
I hope, because this is end of the week or end of this session, this NPTEL course. That's why maybe people have dropped or they'll be busy with the other exams.
Yeah, some universities are conducting exams also for the students.
Yes, their college and state exams
Yeah, state
would
exams are
be
going on.
almost around the corner. Yeah. I'm assuming you have gone through this week's lecture, right?
No, Vivek, not yet. Uh,
Okay, I
I'm
can
also,
address you as Anand.
yeah, Anand or Devanand, both will be fine.
Okay.
I'm
Okay.
from
Thank you.
faculty discipline only.
Okay. You prefer me calling you professor? It's all right.
No, Anand will be fine.
Okay. Thank you. Let's wait for 2 more minutes and we'll get started.
Yeah, sure. We have one more session from 5 to 6,
Yes.
which has been announced. That will also
Yes.
be taken up by you.
No, there is a student. We are all PMRF students. So he
Okay.
is also a PMRF student. His name is Nilesh. He'll be covering the same topics that I'll be doing, but he in his own teaching style.
Okay.
So it's good to attend both. You can
Yeah.
attend either one, or if you're comfortable with the assignments, it's not a necessity that you need to attend these sessions.
Well, I think if we attend it, a reputation will be helpful for us.
Absolutely, that is your personal call.
Yeah. Because we are new to this conditional probability field.
I think you must have covered conditional probability at some stage or the other. But anyway, I'll just touch upon them.
Sure.
Okay. So it's 4-8. Let us start. Yeah. So the first thing that we'll discuss is conditional probability. Now, given we know what a probability is, it is the chance or an chance of an occurrence given a space. So if I have, um, space all of these are possible states. I have something that I'm interested in. Let's take A, there is B, there is something like C. Yeah. So when I say probability of A, what I mean is that how likely is A to occur. So this is going to be something that ranges from 0 to 1. Either it will not occur at all, or it will occur with the definite 1, right? So I'm sure that it's going to occur. So this is what 1 is. Anything in between just gives the information of occurrence. So what conditional probability means is that I have what I want to find is probability of an event A given that another event has occurred. Now, when we do this, this is not going to be simply, let's take probability of A or divided by probability of. It's not going to be something like this. Yeah, sorry. Why is that? Because we need to find the probability that A and B are occurring together. That doesn't mean at the same time, they can be in sequence, but given that I need to find probability that A and B both has occurred, right? So that is the probability of A intersection with B. So that is the region. Let's take another new diagram. This is B. Yeah, I have one more here. Okay. So this is the region where we call A intersection B. So the probability of this occurring divided by the probability of B. And why is this? Let us go the reverse way. What is the probability of A intersection B? What I'm trying to find is that I want the probability that these both has occurred together. So the probability of this A intersection B would be A intersection B, the set, and then divided by the space. Right? So this is something that I'm interested in, and how can I make this? Is that B? Sorry, let me make it A intersection B. A intersection B. Now, yeah, A divided by yeah, intersection with B, even B by tau. Yeah, omega, capital omega. Now what I do is that divide it with omega again. Now nothing is going to change because of this division. I would have yeah, okay, it's going to become the same. Let me just reiterate it again. B by, yeah, let's keep it in this form. What does this mean? This essentially means that B has occurred. I am finding the occurrence where A has also occurred. So this would be nothing but P, A by B, and this is your PB. Okay? So this is where it this formula comes from. So let us try interchanging A and B. Again, B intersection A must give us probability of B, condition that A has already occurred, and probability of A. So since we know that intersection commutes, right? commutes. Okay, let me just put it this way. Intersection commutes. That means that A intersection B is equal to B intersection A. Because of that, I can equate these both equation. With that, I'll get my base rule. Base rule from 1 and 2 at 1 equals 2. I would get P of A by B, or A given that B has occurred, will be probability of B given A has occurred, probability of A divided by probability of B. So this is my base rule. I'll be using this when we have to estimate the probability of a state given that certain things have occurred in the history of it, or given there is another measurement that is being doing. Like let me come directly to robot model. So for a robot, I would have its state variable, right? So this is the let's take absolute value that I am sure of, right? And then there is a measurement. Okay? So there can be stochasticity in the measurement and also in the state variable. Like this concept of absolute is what we are trying to deal with. We do not have an absolute state variable. So here, what it means in a robot setup is that given I have given an input, that input in controls we use the variable u, and given I have given the signal, has the state variable moved from, let's take x t minus 1 to xt. So this there is some stochasticity here that prohibits me to take the sensor value directly into my model. So there is where we do a measurement. So this is the sensor value, and we treat these both state variable and measurement different. So what my measurement would be given by the symbol capital Z. Let's take at a particular state, or let's take a time quantization we have done. In that time, the measurement that I do, let's say t, will be the measurement of the state. So this is what I can rely on, right? This information. Again, there can be randomness in this information. This will be given to you. What is the probability that my the value that I have tested? Let's take I am testing for 1, the value 1. I am searching for 1. So what is the probability that I'll get 1 given that it is actually 1? I'll get that information. What is the probability I'll get 1 given that actual variable is 0? This is the um, false positive case. Yeah. So there will be another state, something like 0. What is the probability of 0 actually being measured, and what is the probability that it is not? So these information will be given to you. So let me just get down to state probability. So a state's probability will be P of the state is X Right? So I can denote this as the state's probability. Now we will define something called state's transition probability. Transition probability. So what this gives me is that probability of x at t, let's take time, given the model has gone from 0 to t minus 1 for an input history of 1 to t and a measurement that is being done from t 1 to t minus 1, right? So why is it t minus 1? Because at x t I have not measured my quantity yet. So that is the state transition probability. So had I had t, that means that it has saturated and state's probability will become something like probability of x t given that x t minus 1 is known, right? Yeah. So now we make an assumption in our model that all of these models that we have described, this robot sensor data and all that, follow Markov property. Hmm? Markov's property. So what Markov's property states that for the probability at a state, I do not require the state or the history of things that I have done to come to this state. So that is what Markov's property would state. So that is probability of x t given that x t minus 1 has occurred. So having this, this means that probability of x occurring from that entire space, because that space, even if you iterate continuously, you will still remain in that space. So this would mean that what is the probability of x occurring? Let's take head and tails. I keep on flipping it until I get tail. So the moment I get tail, I close it. I don't go on iterating further or flipping this coin further. So there is no input from me. So that is what this model would give. So here, the conditional probability is that xt given xt minus 1 has occurred with a signal of ut, and this ut is different from 1 to t. What ut means is that at after time t minus 1, right, the signal that I have given is ut. Right? Yeah. Similarly, we'll have something called measurement model or measurement probability. Right? So here I'll remove this transition word later. First, we'll see how it is not being affecting. So I have the measurement at the time t. Let's take time t. I have the measurement given that my state has gone from 0 to t, and I have given a control signal from the first iteration or first instance where I try to modify the system, give input, that comma 1 to t minus 1. So what this represents is that the probability of the new measurement at time t, given that my state has moved from 0 to t, u has gone from 1 to t, and my measurements are also made from 1 to te minus 1. Why is it t minus 1? Because I'm measuring currently t for t. Yeah. So assuming Markov property again, here you can see that such a probability would be fixed, right? So I am not interested in um, the, okay, let me put that I'm interested in that also. Yeah. U t, right? So Markov property will give me this, because this is the history. I'm letting it go, right? So here I can say that one thing is that the probability of ZT measurement is not going to depend on your control signal. They have to be mutually non-interacting or exclusive. That way you can take. Why is that? Then my sensor model will never be reliable. My sensor information, if it depends on the control signal, it's not going to be reliable. And what I mean by depend is influence. Like ZT, that you can be measuring UT also, or something like that. At that time, it will be valid, but what I mean is that UT has no influence on ZT. So from there, I would get probability of ZT by XT, which is going to remain fixed throughout this time interval 0 to t. Right? Yeah. So now we introduce the concept of belief. Belief as something that is the internal information of your system. Right? And this belief is what you are interested in. So this belief is going to, if this belief tends to 1, you take that your system has reached that particular state. So this is what it means by belief equals 1. So this is the output that you will be taking. And how are we going to calculate it? We'll discuss it now. The belief of xt, it's going to depend on a state, that will be equal to the probability of that state given z, or measurement is being done from 1 to t, and you have given a control signal of 1 to t. Now again we can assume Markov property and simplify this model, is that I'll get probability of okay, let's not put Markov property here. Let us expand this, and then we may use something like a Markov property to simplify our application. Okay, so yeah, let me just check it once. Yeah, it is correct. So in order to get to belief, we do a belief prediction. This is the anticipated value that we have at let's take xt. Right? Okay, yeah, xt. So this is not at t. Okay? So this does not depend on the state t at t. Rather, it depends on t minus 1. It is predicting about xt. Right? So that way we can take that probability of xt given the measurement is made from 1 to t minus 1, u a control signal from 1 to t. Here you can see that I am using u from 1 to t. So this does account that after you have taken the or after you have given the ut signal in the t minus 1 iteration or t1 minus 1 time, you have given ut, and after that you are predicting your belief, right? So this is crucial for base filter algorithm, right? Or it's known as base algorithm. Is there any doubt till now?
Yeah, I have understood this.
Okay.
We can go ahead.
Yeah. I'll thank you for that. So the prediction term, what I call is belief dash xt. Let me just copy down. Right. So this um yeah. Now what I'm going to do is manipulate this in a way that I introduce an integral. Why I'm doing that is because the probability that we have at ith or t time, right, is an accumulation of what I have done previously. So that information has to go into this formula. So what I'm basically doing is that this 1 to t minus 1 and 1 to t, I'm making it as a integral to estimate the probability. Yeah. So I have p of x. I can express this. This is a manipulation, right? I can express this as p of x given y has occurred times probability of y dy. So this integral again, like for y, this will be a definite integral, but I'm not sure about the limits. Okay, no, it's going to be an indefinite integral because we are taking time that is tending to a really long time, right? After that, it would have saturated, so I would get the probability of that state, right? So, how are we going to change this probability into an integral? Is that we will introduce probability of state at t given I know probability of t minus 1, sorry, the state t minus 1 has occurred, and I have given a signal from 1 to t minus 1, the same, and a signal from 1 to t. Okay? So this will be our y. This x t minus 1 state is nothing but the y. So when I have multiple conditions, I am spacing them with a comma. Right? So this will be times probability of x t minus 1 given, right? Yeah, z 1 to t minus 1, and u has gone from 1 to t minus 1, because when I'm estimating t minus 1, I have not given, when I'm finding the probability of t minus 1 given this condition, ut has not occurred. This will be times state at t minus 1. So this will be integral over that. Right? So here we assume Markov property. Right? Markov's property. We would get something like this, that probability of xt given, I am not concerned about the history of measurements that has been done. I am not worried about the history of measurements or control signal that was given. What I'm interested in is the current state, right? T minus 1 comma ut. Right? So this zt minus 1 is not going to influence my probability, and that's why Markov property, upon adding Markov property, this will go off. So now times probability of xt minus 1 given zt minus 1 has occurred upon a signal of ut minus 1. Right? I'm not concerned about the history from 1 to t minus 1, and this is also one history of 1 to t minus 1. I'm not concerned about them because of Markov property. Right? So this will be times xt minus 1. Right? So here is something we have already seen. Let me just bring it back here. So this is nothing but our belief. So here we can say that probability of xt given xt minus 1 has occurred, and I've given a control signal of ut, and this is times the belief at that state, or t minus 1, the belief of that state just previous this iteration, right? So we will have xt minus 1. Yeah, continue. Right? So this is our belief prediction as BL will be an integral x of t xt minus 1 ut belief of xt minus 1 xt minus 1. Right? So let us now simplify the belief equation. Right? So the belief that I have is equal to probability of xt given that I know z 1 to t and u 1 to t. Right? So this is my belief equation. Right? So this I am going to apply Bayes rule. It's a rule, not a rule, not rules. Okay. So we will have probability of xt, since this is b, divide given condition that xt z I to t minus 1 u 1 to t, right? And then probability of a. So what I have done here is probability of this measurement provided this has occurred, right? Yeah. So probability of xt given said I have I to t minus 1 because I am doing um, the estimation of zt. So here it will be a time series or history from 1 to t minus 1. comma u 1 to t. We have not tampered u, so u preserves as it is. This is divided by probability of b, that is z t given z1 to t minus 1 has occurred u1 to t, since we are not playing with u now. So here I can take this one as a value like eta, because the prediction that you're doing, or the probability that you're calculating, we have assumed that it is not being dependent on the control signal, right? So the probability of zt, let's take this is head, the previous measurement was tail. The probability of head, given that previous iteration or previous um, time step, I had tail. So that is going to be a fixed probability, and that is denoted by eta. So now I can just simplify this equation, eta times probability. Again, I'm assuming Markov's property. Right? I'll have probability of zt given yeah xt has occurred times probability of xt given z1 to t minus 1 is known, u1 to t's has occurred. This both has occurred. Now why I'm taking this as a time series, not as a Markov property, is because again you can make this expression in terms of this, so that time history is going to stay. So only thing that only where I can apply Markov property is this, right? So here you can see that this is nothing but my prediction. So I will get eta times probability of zt xt given xt times belief prediction, right? And here you have to note that it is at xt, right? As contrast to here, the belief was xt minus 1. So what my current belief will be, it will depend on the prediction you have made and the probability of that measurement occurring, given that that state has occurred, right? So that is how we are getting our belief equation. Belief of xt will be eta times probability of zt given xt has occurred times belief prediction of xt. Earlier, belief prediction is a summation of probability xt, occurrence of xt, given that xt minus 1 has occurred, right? Times the belief. This belief is actually the information of the state that we know is true. Right? This is what we can trust on. Times the belief that was there in the previous iteration. So now it makes complete sense of how we are adding this value. Like it's an integration, so we can always discretize as a summation. Yeah. So with this, we'll get into Bayes algorithm. Bayes algorithm. So what we do first is estimate prediction, right? So let us have um, prediction of state x1. Okay, let me not make it state x1. So let me just define x0 is the state at time t is equal to 0. X 1 is nothing but time t is equal to 1 second. Let us take for this case. So this is what I mean by x1. So this x0, let's take for head and tails like we spoke about. The x0 can have two states. One is head, other is tail. And the same goes for x1, either head or tail. Okay? And same for x2 and so on. But what we are trying to do is that find a probability that this has occurred. Right? So like this, you can scale for any sensor data, like whether the in the lecture it was put forth whether the door is closed or open. There is an assignment problem on it. I think this will solve it. So here we write that belief of x1 is nothing but belief, sorry, prediction of, yeah, let me just write it again. I don't have enough space. So this is going to be integral of, so let me just keep aside that integral symbol. Let me see what is inside the integral, that is the integrand. That's the probability of x1, given that you have given a control signal of u1 comma x0, because I'm measuring this, right? So this is nothing but my measurement, right? So my z can be that head is a measurement, but the actual value was head. The actual value was head. My measurement is head, but it was tail. My measurement is tail, but it was head in reality. Right? My measurement was tail, and it was actually tail. So this is the measurement. I can always simplify this one in terms of x naught so that it is easier for me to understand. So here I will just give a condition that it was open, and that way I can find probability of it. So this times the belief that it was there in the previous iteration. One second. Yeah, I have done a mistake in my notes. So yes, belief of x0. Right. So now uh, this is for x1. For belief xt, okay, this will be plus belief of x0, right? Because that was our first belief where we started with, right? So that will be actually it will be yeah, it will be 0. Let's just take it out. So now I'll have summation from 1 to t probability of xt, given that ut and xt minus 1 has occurred, belief of xt minus 1, right? So you may be wondering, where did the dx go? This is actually taken into consideration when you do a summation. You assume that this probability is not a probability density as compared to the integral. Yeah. So because of that, this has the information of d x t minus 1, but then it is encapsulated in this formula, right? So with this, we are almost at the end of this concept. So given I do for time 0, sorry, for time 0, I know the belief, right? This is what I start with. This system, like this is what I start with. This information I know. That probability, let's take belief x naught is equal to head. I know that it's likely, it's highly likely that head is what I'll start with. So I'll get something like this. This is known. This is something I start with, right? And x0 tail will be 0.2. So generally we start with an unbiased position as 0.5 and 0.5, and based on our model information, we will update this to get the actual state. So what we are trying to do is that we are making this belief about this state tend to 1. It may not go near 1 because you would have given a larger control signal, and because of that the state would have gone somewhere else, the position would have gone somewhere else. So you'll have likely a probability less than 1, right? So yes, um, yeah. So based on the prediction of belief, we calculate belief at xt as eta times probability of zt given xt has occurred times belief prediction xt minus 1. Okay, sorry, xt. Right? So how do we get this eta parameter? What we do is that at any um, given iteration or given time step, let's take, we'll take 0, right? So there will be, for x0, there are two cases, that is head and tail. So if I do for both, that probability of zt, right? Okay, z0, what is the measurement? Okay, let me just make it x1, right? That way it will be more clear, because x0 it's already 1, right? That's why let me take z1, x1. So probability of z1 given x1 has occurred, this is going to be a fixed value, we know, right? So like I had told here, p by, sorry, z by x head, uh, it is, let's take a sensor that is good in sensing head only. So it's going to have um, probability higher here, right? And a probability that will be lower here. Since these are two cases, actually there will be one, if this is p, this will be 1 minus p, right? Uh, so yeah, so anyway, given that head is measured and head is actually there, I'll get 1, and head given that tail has occurred, yeah, so this will be 0, and similarly here tail and head will be 0, this will be 1. This can change also, right? Maybe a sensor is good at reading positive values than negative values, right? So that in some other case where positive negative is taken, the sensor would have higher bias in the positive um, values. Right? So this is fixed. What is changing is my belief prediction at every time step. Right? So yeah, this is one. Based on this, you can compute for the problems that are given in your assignment. So let's take a case where you have probability of xt given that this okay, let me take an example that will be better. Yeah. So my sensor model is nothing but probability of z being some state head or tail, right? And given that probability of x can also go from head and tail. So now I'll have four outcomes of it. Right? Four. That will be probability of z, that is h, given that x is actually head. Right? So that is 0.8. Right? Z, that is tail. X is equal to head is 0.2. Probability of z, that is head, but the state is actually tail, is 0.1. So 1 minus of head, tail. Yeah. Now my transition model, the state transition model, will also have four cases. Why? My probability of x t, given I have one control, one signal that I'm given, that I'm giving, and x t minus 1 is also, has also occurred. So this will have, um, let's take x. This is the actual, right? X is head, but you have given tail. You have given the signal. One second. Yeah, you have
Vivek,
given a signal. Flip.
excuse
Yeah.
me.
Yeah. Tell me.
Yeah, the second and the fourth lines are repetition here.
Second and fourth.
Yeah, probability of z with t for x.
Yeah. I've made a mistake. Yeah. Right. Yeah. That makes sense. I'm sorry. That was a mistake. So given that I have flipped, uh, and my state before that, so let me make t minus 1 was actually head. So what is the likely probability that I'll get head again? Let's take that is, if it's a biased coin, head biased coin, it's going to be 1, or it's going to be something like zero point 0.8 or something like that. Right? So like that, I'll get three more cases. That is, this is tail, and this is head, this is head, this is tail. Here it is tail and tail. Like this, I'll have four more values, three more values. Yeah. So from this, how do I compute the prediction? Is that, let's take, I am doing for the first time step. After this, I have flipped, right? I have flipped the coin. Given that I have flipped the coin, The expression for this is that summation over 1 to t. Okay, let's keep that aside. Okay, I am really sorry. This will not be from summation over 1 to t. This will be summation over all states. Let's take I from 1 to n. N is the number of states that x has. This is a huge mistake. I'm sorry for that. Because when you see the integral expression, it is integrating over uh, the states in xt minus 1, not dt. Right? So this is what we had done, which is wrong. So that's why I made this correction. Here the states are two, that x can have two states, head and tail. So I will have something like this. Probability of x1 being head, given that, yeah, ut I have flipped, right? Flip, comma, x, like here we have z, we have x, yeah, that is z, but we are getting it, we are converting into x. So given that the measured quantity before was head, right? So this, you'll get one probability of this times belief of xt, that is head. Again, that's 0.5 plus probability of x1 being tail, given that you have flipped, right? And I know the measured quantity is tail, sorry, head. That is not going to change. So we'll have only two values here. Believe that it was tail, right? So this will give me belief prediction of x1 being head. Yeah. Okay, I've made another mistake. Sorry. The x1 will be head. The probability here will be head again. Hmm? Give me a second. The belief prediction will depend on that state, right? Right. For H, yeah, yeah. Now here that it is actually tail. Now, yeah, let me explain this. So, yeah, how do I explain this? Is that given my belief prediction, I'm doing for head. What is the probability that the next time step, the state will be actually head, given that I have flipped the coin, and this time also it was head, times the belief of head, right? State head. Here you'll this part is that I have got head, given that I have flipped it and it was tail before. So this is my belief of wait. Yeah, I've made this mistake. This will be tail. Right? So the belief of x1, um, yeah, the belief of x1 state. So here we are not doing head or tail. So the belief of x1 state is that what is the probability? I think I'm doing a mistake. Doesn't make sense. So yeah, okay. Belief of tail. That will not be the expression. Let me just look it back. Summation over all states. Yeah, yeah. Since we are calculating a belief prediction, so what we are doing is we have belief of um, head, that initially what we had, times the probability that this state is h, that is head, given I flipped, and then I had head. And what is the probability that I have h now? I flip the coin. After flipping the coin, I have h now, but the state was tail. Right? So this will give me the prediction of head in the next iteration. Let's take 1, and that will be probability of x1. Okay, let me just skip this. So now we can calculate the belief of h at state 1. Right? So this is nothing but eta times probability of z1, that is I am measuring head, given that my state is also head, right? So since we have covered that here, head, I'll have probability of 1. So this is going to be 1 times the belief that I have at this particular iteration. So like this you can find belief of tail at 1 given eta, sorry, which is equal to eta, a probability of tail being measured, given that it's actually tail, okay, times prediction of tail. Right? So this makes sense now. Right? Based on this two belief, now you can see that my belief of what we started with 0.5 and 0.5 now would have changed. Now I'll be using these two belief in my computation before. So here I forgot to mention that you will have prediction for tail also. Okay. So like this I'll be computing again for t is equal to 2. And as time, let's take that a control signal, instead of flip, I have something like do nothing. So that means that what state was measured before, it will be now, sorry, what state it was uh, there before, not measured, there before, it will be now. So that way, you can see that your measurement, the error that you have in your measurement, or the randomness that you have in the measurement, will eventually make your belief of head go to 1 given. Actually, I had head. I've done nothing. So let's take time series 1 to 100. I'm iterating. I'm doing nothing in every iteration. So my belief will tend to 1. Right? So this is the concept of it. I think with this you will be able to solve all the questions. Right? Yeah. So there is one question on concept that was given in the previous run. Is that given noise-free measurement, is it possible for robot to know exactly where it is in the state at every instant? So I've recited the question slowly so that people understand. So here the answer is no, because we have discussed that even if you have a noise-free environment in the measurement model, here you would have seen my belief is tending to 1. My noise, my measurement model, like here, I had given some values, but initially I had given 1 0 0 1, right? Even if I have this condition, since we started with a belief that is 50-50, eventually I have got 1. So the answer to that will be no. Yes, Devanand. Please go ahead.
Yeah, I have realized this idea behind it. Probably
Yeah.
once or twice I need to go through this.
Yeah, please do. I'll be uploading my lectures over YouTube. You can refer it again.
Yeah,
So I
sure.
think Sir has covered this really well. So that way, if I have made any confusion, that will get rectified.
Sure.
Yes.
Yeah, thank you.
So you have further no questions?
No, I don't have any
Okay.
questions.
All right. So let me just stop the recording.